Hi everyone, and welcome to the channel. So I recently picked up this Hewlett-Packard 8920A RF communications test set. So the purpose of this test set is to be able to test transmitters, receivers, and of course transceivers. So you can transmit up to 60 watts of RF power into this end connector, but the test set can also pick up very low-level RF signals on this antenna input connection. And there's a built-in RF signal generator and an audio signal generator for testing receivers or the receiving portion of a transceiver. So this test set can make a number of very detailed measurements on both transmitters and receivers. So a very capable piece of test equipment. Now the frequency range that's marked on this front panel is 400 kilohertz to 1 gigahertz, so nice wide usable frequency range. But in my initial testing I found that it seems to work below 400 kilohertz. And I did find some literature that mentions that the test set works down to 250 kilohertz. So maybe going below 400 kilohertz just it doesn't meet published specifications. I'm not really sure, but it seems to have a little bit wider range than what's actually marked on here. Now the serial number on this instrument seems to be a little bit on the early side of production. And later versions of these instruments, the low frequency range stopped at 30 megahertz. And if you wanted to go below 30 megahertz, it had to be modified, or possibly there is an option that could be ordered. But the reason for that change was because of the attenuator that was used. So again, later production doesn't quite have as wide a frequency range unless, again, it's modified. So it is nice that this instrument has that wide frequency range. I noticed that the firmware that's in this instrument seems to be a later version of the firmware, so perhaps it was updated at some point, so that's also nice to have. This instrument is equipped with options 1, 4, 102, and 103. So option 1 is the high stability time base, or OCXO, oven controlled crystal oscillator. Option 4 is the tone and digital signaling. Option 102 is very nice to have. That's the spectrum analyzer and tracking generator. And option 103 is the GPIB, RS-232, and parallel port interfaces, as well as a DC current measurement. So in just a moment we'll look at the back panel, but on the rear panel there's DC current test jacks. So essentially it's an amp meter, and you can monitor the current on the device that you're testing. And right here you can see this front panel is also included. So storage compartment in there as well. So the test set seems to be in good condition as far as the exterior and how it looks. There's no damage on the front panel. It doesn't look like it was handled roughly. There's no dings or dents in the cabinet. So, it looks very nice. Now, when I picked this instrument up, all I knew about it is that it was supposed to power up because the photo that I saw, the CRT had some indications on it. But beyond that, I don't know its operating condition. So when I received it, I had it up here on the bench for the first time, powered it up, and it seemed to be working very well. So I wasn't seeing any problems. The spectrum analyzer display was very accurate. The received frequency, the received power going into the instrument, everything seemed to be working very well. The signal coming out on the RF signal generator and the audio frequency generators, it's all spot on. Again, no problems. And then I was working through some more settings and taking some measurements and looking at the capabilities of the instrument, and then I discovered the problem. So I'll show you that in just a moment and basically what it's not doing. So let me reposition things a little bit here and we'll take a quick look at the back panel. So a quick look at the back panel. You can see the serial port, parallel port, and the GPIB or HPIB interfaces. These are the two test jacks for the current measurement, so up to 15 amps. Right here's a modulation input, CRT video out, so this can drive an external CRT monitor, external scope trigger input. This does have a built-in oscilloscope, 10 megahertz reference output, 10 megahertz reference input, audio monitor output. Over here is just, of course, the AC line in. This can operate on DC voltage as well, so maybe a battery pack for mobile operations, or maybe you're operating it off of a vehicle's power system, something like that. So that's a DC power input, and this is an AC or DC power selector switch. All right, so let me reposition things a little bit here, and I'll power up the test set, and I'll show you what the problem is. So I'll be using this HP8664A signal generator as a signal source when I show you the problem on the HP8920A RF communications test set. So I recently picked up this 8664A signal generator, and like a lot of the test equipment that I pick up, it needed repairs before I could put it into use. So if you're interested in seeing those repairs, definitely check out the 3-part video about the repair. So parts 1 and 2 are about the troubleshooting and actual repair, and part 3 is just finishing up with some final details. So right now you can see the signal generator is set to 300 megahertz, FM modulation mode, 10 kilohertz deviation, a 1 kilohertz sine wave, and the RF is off. So I'll turn the RF on once we're underway with the testing on the 8920A. The 300 megahertz is just a random frequency that I picked. It's not important, and I've tried various frequencies on the 8920A, and it acts the same on any frequency. So again, 300 megahertz, just a random value. The 10 kilohertz deviation frequency, again, kind of a random value. It needs to be within the demodulation range of the 8920A. So, if it's excessively high, it would cause a problem, but 10 kilohertz is perfectly reasonable. And I've tried some different values around 10 kilohertz, and it doesn't matter. So, again, 10 kilohertz is perfectly fine for the test. And the 1 kilohertz sine wave, the modulation frequency, is just a nice easy tone that you can hear. You could also use 400 hertz. That's another common frequency used in testing. I often use 1 kilohertz. I find it very easy to hear that frequency. All right, so once we're underway and doing the testing, I'll try the AM mode as well for the modulation, and I'll show you what happens. And when I make those changes on the signal generator, I'll let you know. All right, so I'll show you the problem that I found on the 8920A. So let me get things started up. So it takes a little bit of time to power up. And there are no indicator lights in the front panel. It's just the CRT display that shows that it's operating. So it takes a little bit of time to boot up. So it should run a self-test. And it's been passing that self-test. Yep, there it goes, it passed. You can see the firmware version is A.15.01, so that looks to be a pretty new version of that firmware. So this is the receive screen, so we'll just go to the transmit screen and we'll grab this adapter. So this is an N to BNC adapter here. Disregard the frequency right now that's on here, that doesn't mean anything. And get the coax from the signal generator. Connect that. Actually, you know what? Before I connect that, what I'm going to do is just go down here to the transmit 0 and just 0 that out. That'll make the transmit power as accurate as possible. That's not related to the problem, though. Okay, so let me turn on the signal generator's output right there. So 300 megahertz, it's being modulated, 10 kilohertz FM, 1 kilohertz sine wave, and 0 dBm output power. So looks very good, 300 megahertz. The time base in here hasn't warmed up yet, so that would settle in over time. And it's after I've had this run for a while, that number does get very, very accurate. So no problems there. The transmit power, yeah, that looks reasonable. If I actually go over here to right here, amplitude there, and then if I just increase this, so there's 1 dBm, and let me go a little bit more, so there's 2 dBm. And you can see right now, so that's 1 milliwatt and then some change, so 1.14 milliwatts. And 0 dBm is 1 milliwatt into 50 ohms. So you can see really it's not even 2 dBm of loss. Go down there, or 1 dB there. Loss, a little over 1 dB of loss in that coax. Makes sense, 300 megahertz, and this is a little over 6 feet of coax, so a little bit of loss in there to be expected. So again, I'll go back to 0 dBm output, and that number is perfectly reasonable. So no problems there. It looks like the transmit power indication is fine. So over here, this is the modulating frequency, so 1 kilohertz, it's right on, no problem. The FM deviation, it should be right at 10 kilohertz. It's fluctuating around a little bit, so if I go over here and just move this to the IF filter, I'll change that to 230 kilohertz instead of 15 kilohertz. And yeah, it looks like that settles in a little bit better there. That's fine. Okay, here's the actual problem though. So again, all these numbers seem to be okay up here, and it's working very well, but this should be demodulating the 1 kilohertz tone. So if we come down here, the squelch is turned all the way down. If I turn the volume up, there's maximum volume. It's dead silent. There's absolutely nothing coming out. So I'll turn the volume back down. If we look at the settings here, everything appears to be correct. So if I move the cursor over, so audio frequency, FM demodulation, and yeah, we can try AM as well, single sideband, some other auxiliary type inputs. So yes, we are trying to demodulate FM. This is a frequency modulated carrier, and there's nothing. Filter is 50 hertz high pass filter, that's fine. Filter 2 is a 15 kilohertz low pass, so 1 kilohertz is between the two filters, no problems there. De-emphasis, not a problem on those settings. Detector's fine. And then this is the audio frequency generator. That's unrelated to what we're doing here. So yeah, I mean, it's just nothing. You know, if I turn the volume all the way up, silent. So let me go over here to the signal generator. I'm just going to switch this off from FM, turn that off right there, turn AM on. So AM is 50% modulation, same 300 megahertz, 1 kilohertz sine wave, 0 dBm. Now I will go over here, let's go to AM. A moment here. Perfect, so 49, and it says it's at 50% on the signal generator, so that's an agreement within 1%. Frequency looks good. And if I come down here, again, squelch is turned all the way down, turn the volume up, dead silent, no demodulation. So definitely a problem. Something's going on there. Now, the other thing that I noticed is that after looking at the schematic, this instrument is supposed to generate a warning beep, and I don't know if it's a beep when you press various buttons or when the beep is supposed to occur, but I've never heard the instrument beep. So maybe it's just an error, like if there's a problem in it, you know, it's like a warning beep, or maybe it's a confirmation, you know, of button presses, whatever the case might be. I've never heard the instrument beep. It seems to me that it's maybe not just the demodulation in here, but more of an audio circuit problem, and it's not picking it up on the self-test. So this has some very extensive self-tests that you can access. If I go over here, just to the test right there, and just as an example, I won't run them all right now, but if you go right here, so the RF, like that, and then you can see the choices. So there's audio frequency, RF, and then some miscellaneous. So if, for example, if I just keep it on the RF, you go down here to that, and then if we were to go to run tests, it's going to try and boot up the basic operating system in here that runs the tests. So again, I won't run all the tests now. I have gone through them and there's no problems, but you can see, you know, this comes up here and there's a whole bunch of selections and extremely extensive self-tests that this runs. It takes quite a while to actually go through all of the tests. So it passes all of those. It's not detecting the problem. So let me show you the schematic, and it has a section with the audio amplifier and some inputs that actually, one of the inputs says beep for the beep tone, and then the audio input and some switching that's going on. I think that's the first place to start looking because we're not hearing anything, and it's interesting to see how they join the beep and the audio signals together on the schematic. Right, before I open up the 8920A, let's take a quick look at the schematic and kind of see what we're dealing with for the audio section. So this is the speaker drive portion, and you can see there's basically 4 inputs. We have the beep tone, the beep high and low, which is in software. You can make that selection if you want it loud or quiet. And then the beep or audio selection, and then it says volume pot, so that's the front panel volume control. So if we take a look right here, these are basically, you can think of them as relays, but they're solid state switches, so they act like a relay. So there's a control signal, and then it passes the actual audio signal through. And these are inverters right here. So we know that either it has to be letting the beep tone go through or the demodulated audio. And if we look right here, beep or audio selection, if we put a signal in here, a logic signal, let's say it's a low signal right here. So you would have a low coming over here, but this would invert that to a high right here. So if this is a high over here, then this is a low right here. So it's essentially selecting one or the other of these 2 analog switches. All right. So let's say that this is selected. Well, then that means this one is not. Well, then that's the demodulated audio right here that would pass through, would come over here. And you can see right here there's 2, they essentially look like op amps, but they're audio power amplifiers. It says LM386N, very common amplifier chip. And it's being used in the bridge mode. So the audio signal's coming in and then just going through a very classic type of audio amplifier circuit. And then you can see right here it says speaker, and those are the outputs to the speaker. Also note that neither side of the speaker is grounded, so if we take any measurements on the speaker, we don't want to cause a connection to ground, which would essentially short things out because both speaker lines are floating. All right, but going back over here, if it selects the beep input, then this is not selected anymore, and it would be right here. We have the beep signal coming in, so capacitor just for coupling, signal comes through. Now there's the beep high and low. Well, it's the same thing. If this is a let's say a high signal coming in right here, then this is a low right here. If this is a low over here, then this becomes a high at this point. So it's selecting one or the other of these two analog switches. So the beep signal comes in, let's say this one is selected, so some attenuation right here on this resistor, and then it comes through, let's say this is selected, it comes over here and comes down, this has been selected, comes out, and the beep signal goes out. But if this one is not selected, that means that this one must be, and so what happens is right here, the path comes down, you have some more attenuation with two resistors. This goes to ground right here, and then the signal comes over, so this becomes that lower level of audio signal for the beep tone would pass through, and then the same path, this would be selected for the beep tone, and it comes over and gets amplified and goes out to the speaker. So really straightforward design right here, and because we're not hearing anything, the beep tone or the demodulated audio, I'm wondering what's in common to all of this, and kind of think about that for the troubleshooting. So let me get things opened up. Let's take a look inside the instrument and see what we're dealing with. All right, let's get the 8928 opened up. All right, and we're in. Let me reposition the camera a little bit here. So, of course, it's standing front down right now, and that's why I put the cover on here. So, this is basically the top of the instrument. Just leave it this way, you can kind of see around inside of here. A little bit here, let's turn that up. Touch that up a little bit. So, wow, that's really dense construction in here. I mean, that's really solid. So, a lot of shielding on everything. So it looks like a lot of modules back here. And some stuff going in there. So it looks like probably some long boards that are down under this cover here. More boards in this cover. CRT assembly right here. Some heat sinks over here. It's probably power supply. The AC line is going in this upper corner. So power supply over here. So it looks nice. I mean, it looks really clean in here. So turn things around here, and whoa, what in the world? Look at this. Look at this. Let me get you zoomed in here. What the heck? It's crusty old foam, but that looks like where the speaker is supposed to be. There's no speaker. What in the world? There's two wires with like duct tape on them. What the heck? Somebody took the speaker out? Why would you take the speaker out? That's the craziest thing. If you didn't want the speaker, maybe for some reason you didn't want any audio, you can just unplug it right here. But somebody removed the entire speaker. And then this old looking foam, there's like a metal bracket right here. So let me get you zoomed in a little bit closer. You can see all the way in there. And I'll turn this, maybe a little bit better light on it right there. Like that. Look at that. So this foam is kind of, I don't know what that was, around the speaker or something. I don't know what else would have gone here. I mean, this looks like a spot where the speaker would go. And actually on the case, yeah, see right here on the case, it looks like there's a cutout, this area right here. So I think that's where, that would match up to this area right here. Well, that's unexpected. I think what we should do is put a test speaker in here and see, does it come to life? Is there any audio? Or maybe, let's say, hook up the test speaker and maybe it goes berserk and, emits some terrible sound or something, and maybe that's why somebody took the speaker out. Maybe it was acting, really in a bizarre way. But, I mean, it's like duct tape on here. I mean, that's not that great. It's kind of like a metallized looking duct tape. Nice for short circuits and who knows what else that might cause. Interesting. Well, again, a little bit unexpected on that. Now the problem is, of course, finding a speaker to fit in here, because this is a real specific size. So I know I don't have any really small speakers like that. I have a test speaker that I can just clip into the circuit, and we can try things out here and see what happens. But I'm going to have to see what I can do to get a replacement speaker. To be honest, I would rather deal with electrical problems rather than missing components like a speaker, because let's say those audio power amp chips were defective. You know, those could be had. That would be an easy fix. A speaker like this, I don't know, finding a replacement. So I'll have to look into that. But let's see if there's anything else going on with this. I'll get a test speaker and I'll get that hooked up, and then we'll hook it back up to the signal generator. I'll put that FM modulated carrier at about 300 megahertz or so, like we were doing before. Put the 1 kilohertz tone, and let's see if we get any sound out of this. And that'll give us an idea if there's more troubleshooting, or are we only dealing with a missing speaker. Now, while we're in here, let's just finish looking around on the back side, what would be the bottom of the instrument here. So it looks, just at first glance, pretty clean. Make sure it's touched up there, just kind of on the bottom here. So the boards look okay. It's not too dusty or dirty. That previous 8664A signal generator repair that I did, if you watched that video, you saw the amount of dust that I had to clean out of that instrument was just crazy, just balls and piles of dust literally rolling around in the instrument. Nothing like that going on here. This looks quite clean, so that's good. I mean, it looks nice inside, but yeah, I thought that was pinched there, but no, that's just formed. So yeah, no, nothing looks damaged or anything. Let me grab a flashlight real quick here. I'm going to look in this power supply, just so I can kind of see inside here. I'm looking at the capacitors in there, so I'm not seeing tops of capacitors. I'm not seeing anything looking bulged or anything that stands out, again, just at first glance, looking in the power supply section. And of course, we know the instrument powered up, so it does work, but yeah, that looks okay in there. Looks like a switch mode type power supply. Looks like, right, I don't know if I can get this on camera. It's buried under there. There is a RIFA capacitor right there. Those are notorious for problems. So what I'll do is I'll try and get a picture of that, and I'll just put that up on the screen so that you can see it. But that's going to have to be changed. I definitely don't trust that RIFA capacitor. So those are known as safety capacitors. I did a video a while back about safety capacitors and also about RIFA capacitors and the fact that they fail. So if you're not familiar with a RIFA capacitor, that was a brand name. Now they're sold under the Kemet name, K-E-M-E-T. I think they've basically solved the problems that they had years and years ago, where the capacitors, over time, the housings would crack and they would get moisture inside of them just from the atmosphere, and it would cause the internals of the capacitor to disintegrate, and they basically become a resistor. They short out, and you have all kinds of problems. They literally go up in smoke like a little bomb. They just go off. And I've had many of them fail over the years in oscilloscopes, in power supplies, and many different manufacturers use RIFA capacitors. To this day, they're in use. If you ever come across an old RIFA capacitor, you definitely want to change it. So again, this is 1990s vintage instrument, and you definitely want to get those replaced. And even if they don't look cracked or anything, it's a good idea to replace them. And if they have visual cracks in them, they're just a time bomb waiting to go off. So anyway, we'll have to get this disassembled, so that'll be something else to do as well. And given how this is all kind of tucked in here, I'm not exactly sure what's required to disassemble this and get that power supply out, so I'll look a little bit closer and deal with that. But first thing, let's take a closer look. I'll get a speaker hooked up and see what happens. So take a look at this. When I remove these two pieces of metallized duct tape, this wire that went to the speaker still has part of the speaker terminal on it. It's crazy. It's like someone literally ripped the speaker out of here, and the wire is still soldered on, and this is part of the speaker terminal. And this wire is like it's stripped back. There's a lot of bare wire on the end, so maybe it was cut off of the terminal and then stripped back, or whatever the case may be there. But this one, how odd. It's like the speaker was just literally yanked out of here. So with this broken, if someone was taking the speaker to salvage it, it's basically got a broken terminal board on it at this point. So why would you do that? Really crazy. I've never really seen a missing speaker in a piece of equipment like this. I've seen damaged speakers where the hole gets punched in the cone or something like that, but where it's just completely missing like this and just almost like it was yanked out of here. Really odd. I'm not sure what was going on. Alright, I have a test speaker connected right there. Some test leads just clipped onto the wires that were broken off of the other speaker. So this is an 8 ohm speaker, far larger than it needs to be, but it'll be perfectly fine to do the test. So let's get this powered up. And I'll get this adapter on here like before. Ah, there's a beep. Well, we sure didn't have that before. Okay, so this is all self-test passed. Looks good. So let's go to the transmitter screen right there. Volume is turned down. Squelch is open. All right, so I'll go to FM modulation like before. Let's get that turned on. Right there. RF is turned on. Okay, 300 megahertz. Same readings as we were seeing before. Probably need to move this over. Oops. Let's go. Let's see here. Okay, that's fine. So that's on FM demodulation. Okay, I think it looks good. Hey, there it is. Had a little scratch in the volume control, but now that seems to be gone. It works. How cool is that? Very cool. So I think if I turn this off, what this should do, let me turn off the modulation here. Turn the signal generator off. Let's try this. Yeah, so with no RF input, you just have the rushing sound that you have with FM. So, and then the squelch. Yeah, and then the squelch closes like that and silences everything. Perfect. Well, excellent. It seems to be working. Let's try the AM. So over here, let's turn this FM off, go to AM, on, and over here, let's go, where do we want to go? Right here. So, okay, there's AM. There it is. Perfect. So it demodulates the AM as well. Very cool. So the instrument seems to be working. The next thing I need to do is get into that power supply and change out that safety capacitor, and I'll get that squared away. Looks like a little bit of disassembly to even remove that power supply, so I'll check that out and see what's involved there. And I need to see what can we do about the speaker. You know, a small speaker, yes, but it needs to mount correctly, or something needs to be made to make a speaker mount in there that if it's not original. So what I'll try and do is find the original type of speaker, see if that's even available. Maybe someone has one of these that they've salvaged parts from. That would be ideal. Maybe I could locate a used takeout. So there's one other thing I thought I should check before I start disassembling the power supply, and I can still do this while the test speaker is connected, and that's the ability of the instrument to demodulate something intelligent like a voice or a music signal rather than just a fixed audio tone. You know, a fixed audio tone might come through and sound reasonably okay, but if there's a problem in the audio circuit, music or voice could sound heavily distorted. So what I've done is I have this whip antenna connected to the low-level RF input, and I haven't actually tried this low-level input. All of my testing has been done on the higher-level RF input. So I've made the selection to use this as the input, and I have this in the manual tune mode, and I've selected 96.5 megahertz. That's a local FM station. So this certainly should be able to sense local FM stations because of the sensitivity on the low-level input, and of course it's in the FM demodulation mode. So if we go here and turn the volume up, perfect. Excellent. So very clear, no distortion or problems. So it's definitely able to demodulate okay. Excellent. Very happy with that. No problems. So it'll always be a mystery why that speaker was yanked out of there. I have no idea what was going on with that. Very strange. So I started removing the power supply assembly, and it seemed to be trapped, and I couldn't tell if it was supposed to remove from the top or the bottom side of the instrument, and it was also hanging up on some other components. And then I realized you have to remove this very well shielded input assembly. So you can see on this assembly there's two B and C connectors on the side, and those poke through the front panel, and there's some rigid coaxes that attach to this assembly as well as a ribbon cable, and then there's several screws that hold it in place. So that assembly fits in that area right there in the instrument. So with that input assembly out of the way, then you have the needed access to get the power supply assembly removed. So this power supply board fits onto that L bracket. That L bracket acts like a heat sink, and I'll freshen up that heat sink compound when I put everything back together again. There's some power transistors on the board that are, touching the side of that L bracket, and there's some clips that hold everything in place. Then there's a smaller circuit board right there that plugs onto this board, and then this back piece right there fits across the L bracket. So a fair amount of disassembly to get everything apart, but definitely worth the effort to replace these RIFA capacitors. Now you can see on this L bracket all those little standoffs that are on there. So those are like a little one-way clip that goes through the holes in the circuit board, and there's also some screws that hold this board onto that bracket. But these little one-way kind of clips that are on there are a little bit tricky to remove because you lift one up and then you go to the next one and the first one wants to snap back down again. You can really only flex the circuit board so far. It's easy to put back together again because you put the board on all of those clips and just press it down and it all snaps together at one time, but it's impossible to remove all of them at once. So again, a little bit tricky, but everything's apart, and now that it's disassembled, you can see right here I have two RIFA capacitors that I've desoldered. So there was a second RIFA capacitor, this small one, and it was hiding on this board. I couldn't see it when it was installed, but did find it once everything was taken apart. So these two RIFA capacitors don't have the cracks in them that I often find in some of the older RIFAs. A lot of times they're almost to the point of crumbling and just falling apart. So these don't look that extreme. Would I trust them? Absolutely not. Here in 2025, as I'm making the video, it's at least 30 years old, so they definitely need to be replaced. And I really can't stress enough how important it is to replace these RIFA capacitors. You find them in lots of different consumer electronics. I have a vintage, probably 80s era, I would say, TIAC reel-to-reel tape machine, and it had one of these RIFA capacitors across the AC line switch. So they turn up everywhere. You just never know. So if you find one, definitely replace it, because when they fail, they do so catastrophically, and they can cause a lot of damage to the board and surrounding components. So definitely want to take care of them before that kind of damage happens. So to replace these two RIFA capacitors, I'll be using these as the replacements here. These are made by Chemet, and Chemet is making the RIFA brand now. But if you take a look right here, just a little bit closer. So I won't go into the details about safety capacitors because I made another video, and if you're interested in learning about safety capacitors, check out the video that's titled Failing Safety Capacitors or Failing RIFA Safety Capacitors. I'm not sure exactly what the title was on it, but you'll see it in my list of videos. And I talk about the RIFA capacitors and also what these different classes of safety capacitors mean. So this particular capacitor is a 2200 picofarad, and you can see it's an X1 Y2 class, so it meets both of those classes, so it's appropriate for replacing the original Y class capacitor, and so this will work very well. And like any capacitor, the replacement needs to have an equal or higher voltage rating, but with safety capacitors, they need to have the correct class rating as well. So again, check out that video if you're not sure what the classes of safety capacitors mean and the other details about them. And right here, here's the other one. That touched up a little bit there. So you can see this is an X2 class, and it's a 0.047 microfarad. So let's take the two old RIFA capacitors and I'll connect them to the Sencor LC102 and let's see how they test electrically. Even if they test out okay, would I trust them? No, because again, they're going to fail eventually. They always do. So you absolutely have to replace them. But it'll be interesting to see if these are holding up electrically or have they degraded some. And we can compare them against these brand new ones, make the comparison. Also, I'm using the term safety capacitor, and I know in the comments on the video that I made about the safety capacitors, there was a lot of conversation about that term safety capacitor. Some viewers were saying there isn't even such a thing as a safety capacitor. Don't call it a safety capacitor. Well, you can see on here, right here, this is Mauser Electronics, and take a look right there. Safety capacitor. That is definitely what they're called. But why are they called a safety capacitor? What's so safe about them? What are they doing? Well, it's the way that they're supposed to fail. And safety capacitors are supposed to fail in a safe way, in a known way, basically. So a random capacitor that's not a safety capacitor, if it's subject to an overvoltage, who knows how it's going to fail? Would it be a short circuit? It's just unknown. Safety capacitors are supposed to be designed to fail in a controlled and known way, and in a way that doesn't subject the user to a shock hazard. A bit ironic because RIFA capacitors are going up in smoke and going off like little ticking time bombs, not exactly safe. So yeah, I get that idea, that RIFA capacitors are anything but safe. But anyway, that's a little bit about the term safety capacitor. If you hear that term, or what exactly does that mean? That's what's going on there. All right, let's go over to the Sencor LC102 and take some measurements. All right, let's use the Sencor LC102 to check the old RIFA capacitors and then compare to the new capacitors. So on the Sencor LC102, I have it on the all other capacitor mode. Obviously, it's not electrolytic or tantalum or something like that. And then we'll start with the 2200 picofarad first, and so that value's been entered in, so it knows the expected value. And then 275 volts is the voltage that will be applied to the capacitor for the leakage test. And I have the tolerance set as plus minus 20%. That's pretty typical. I think the old RIFA capacitors were probably rated that, so that's a good starting point. So that'll give a go, no-go indication if they're outside that tolerance range. So here's the old RIFA 2200 picofarad right there. So let me get that connected. Test leads. And also the test leads for the lead 0, open and short, has already been taken care of. So if I just take the test lead, and I think I can just kind of put it right up here, like so. Oops. Let it stay there. That's fine there. So that you can see the capacitor right there. Okay, so let's do the capacitor value. Well, that's not off to a good start. So it says bad. It means that that value is outside that plus minus 20%. So that capacitor is drifted a bit. And for the leakage test, let's try that. So it's normal that the value starts a little bit higher and then would drop down. And ideally it should go to 0 for the current. So right now that's 0.13 microamps, 0.1 microamp. And it says good, so it's falling and it looks to be okay. Let's give it a little bit of time and see if that goes all the way down to 0. So again, that's putting 275 volts on that capacitor. 0.03 microamps, 0.02. So the initial current is a little higher as the capacitor charges. Of course, 2200 picofarad is a very small value, but yes, it did fall all the way down to 0. So that capacitor electrically, it's not too bad, although it has drifted in its value a bit. So that's somewhat of a problem, but it doesn't have excessive leakage. And when you hear leakage on a capacitor like this, that's leakage current that's flowing through the capacitor. Essentially, you could think of a fictitious resistor in parallel with that capacitor. So some current is passing through the capacitor, and ideally it should be blocking all DC current. So the initial charge and then no current flows after that. So when you hear a leaky capacitor, electrically leaky, it's not physically leaking something out of the capacitor. Of course, something like an electrolytic capacitor, yes, they can leak things out as well, but in this case, when we talk about leakage, it's electrical. Okay, so let's go to this next one here. So I'll go to the new 2200 picofarad right there. Set this up here. So you can see the capacitor sitting back there. That's okay. It's fine there. So capacitor value, yeah, as expected, it's good. So it's within the plus minus 20%. No problems there. And let's go to capacitor leakage. Perfect. Look how quickly that fell, almost down to 0. So faster than the old capacitor. Yeah, now it's already at 0. So that other capacitor achieved all the way down to 0 for the current reading, but it took a little bit of time to get there. And this capacitor very quickly charged up and then has no further current. So that's how it's supposed to be. So very good. So not surprising that that old RIFA is not testing as good as brand new capacitor. Alright, so this is the 0.047 microfarad, the old RIFA. So what I need to do on the LC102 is change the value, so we'll go 0.047 microfarad so it knows what we're going to be testing. The voltage can stay the same. Just get this clipped on here. Set that there like so. Okay, so let's do capacitor value. So it says that it's good, no problems there, so it's within the plus minus 20% tolerance. That looks fine. And let's do leakage test. .62, 0.51 microamps, 0.45. Is dropping. No, it says that it's bad. So that value is taking too long to fall down, and 0.32 microamps, 0.3. Give it some time here, but that really should be very close to 0 already. So it's just, it's taking too long to fall, and then the meter knows that. That's why it says that it's bad. It's taking longer than expected. Yeah, it's really not falling all the way down to 0. So that capacitor is electrically leaky. Again, you could think of a fictitious resistor across that capacitor in parallel, and that's the path that the current is taking. There's current that's actually flowing through the capacitor, and of course the capacitor should be blocking all DC current. So yeah, it's really having trouble falling all the way down to 0. So not surprising. So this is an example of a failing RIFA capacitor, and it's only going to get worse. Eventually, this is going to start passing so much current that it begins to overheat, and it literally will go up in smoke and basically explode. All right, so that capacitor is obviously starting to fail. So here is the other 0.047 microfarad, the new one. So put that on the test leads here. Okay, let's try the capacitor value. Perfect, no problems there. Very close to the expected value. And try the leakage. Look at that. Compare that to how the RIFA was performing. Look at that. It's all the way down to 0 already. That's how it's supposed to be. Perfect. As expected, a brand new capacitor. Chemet makes very good quality capacitors, and this one is obviously working the way that it's supposed to. So excellent. So the next thing that I'll do is get these capacitors installed into the power supply, reassemble the whole power supply, and we'll continue on. Here we are a number of days later. So I have the power supply reassembled and back in place. The input module is installed. The interconnecting cable and the rigid coax cables are also installed. Now I wanted to check the memory hold-up battery to make sure that it was in good condition. And you can actually see the memory battery through this cutout area in the circuit board, but you can't test it from this location because you can only see about half the battery. So you have to remove the board to test that battery. So it turns out that the battery did test okay. It was as good as the day that it left the factory. But to remove the control board as well as any of the other circuit boards and modules, you have to do so from the top side of the instrument. So again, this is the bottom of the instrument. And as we saw earlier in the video, there are some shields over the circuit boards and modules, so you just remove those shields and then everything unplugs off of this board. I went ahead and removed all of the circuit boards and modules just for visual inspection, clean up any lint and dust. And there was a little bit, but nothing too excessive, so everything did look to be in good condition. Now, in the middle of the instrument is a cooling fan, and it's very easy to remove that fan once the other modules and circuit boards are removed. And there was a little bit of lint and dust on the fan as well, so I cleaned that up. Now, in this instrument, on the cooling fan, there's a little round metal shield that's attached to the fan. It's about the diameter of a quarter. And it's there so that interference that might come from the fan motor doesn't interfere with some of the other electronics. So I guess there was something about the fan motor that could cause some kind of a problem or interference, and Hewlett-Packard added that little shield to the fan. Now the shield is not on the part of the fan that rotates into the hub and the blades. It's over the label that has the manufacturer's name and the specifications that's on the stationary part of the frame. And it's just glued onto that area. So the manufacturer of the fan didn't make this little metal shield that was put on by Hewlett-Packard or in later years Agilent. Now the problem is that the adhesive that they used ends up drying out, and there's actually a recall or a notice that was put out on these instruments to check that piece of metal and make sure that it doesn't come loose, and because once that's loose in there, you got this piece of metal rolling around inside the instrument and cause all kinds of problems. Now in this instrument, when I took the fan out, the piece of metal was in place, but when I took my finger and just kind of pushed on it, it popped right off. So the glue was clearly old and dried out, and it was just going to fall off at any moment. So I just used a general purpose glue and put it back in place again. Now I'm not sure if all instruments actually have that shield. It may be based on the options or something like that in the instrument. I think I remember reading somewhere that it was used only in certain situations. But if you have one of these instruments, it's a good idea to check that fan and see if it does have that piece of metal. If it does, push on it a little bit and just see that if it's adhered tightly or not, because you don't want that unexpectedly coming off and again rolling around in here would cause all kinds of problems. So check out what arrived. Replacement speaker. So I found this at a seller that has all kinds of spare parts for test equipment. They salvage all kinds of parts and pieces. So they were selling the speaker with the metal bracket, which I already have that bracket that was in the instrument. So let me grab that. It's around the corner here, right over here with the old wire. So this wire, of course, was plugged in there like so, and then this bracket sits in there like that. So that's what we saw earlier. So this speaker is going to go this, get this turned around here like that. So of course it fits in there just like so. Now the good news is that this bracket right here is all complete. And what I didn't realize is that this is actually missing a piece of metal. So I'm glad that I didn't end up just getting the speaker, because that wouldn't have been complete. So if we take a look at this right here, get this touched up a little bit. So you can see how there's two pieces of metal right here that are sandwiched together. So this bracket right here coming out is what we have down there. But there's this second piece that's above it. It has this piece of foam that's attached to it. So this piece of foam is not the same as that crusty old foam that's on there. That's actually sandwiched between these two pieces of metal. But this foam seems to be in good condition. So again, this is a used takeout, but overall, it looks to be in fine condition. I don't see any problems with it. So I'm glad I didn't just end up getting the speaker, because again, it wouldn't have been complete. And if I bring this a little bit closer here, you can see on the back of the speaker, the name and the markings that are on it right there. So once I saw that, it's not made by Hewlett-Packard, or again later years Agilent. It's a third party that they had manufacture the speaker for them. But 8 ohms, 0.2 watts or 200 milliwatts. And it looks like the name is spelled SHIGMA. And perhaps a part number, it looks like BL50AS. And I did some searches and I really couldn't find any reference to that speaker being available elsewhere. So perhaps it was special made for this instrument. But you can see how it attaches with these 4 screws around the perimeter. And a lot of times these small speakers don't have this extra flange on them. So they're just a round speaker like this, and then they attach with a little clip or something else that holds them in place, but you don't always see that flange. So I'm sure a speaker could be found somewhere that might be similar enough to use in here, but I was very happy to find this complete assembly. It just makes the replacement a lot easier. And of course, having that extra piece of metal and completing this is nice, because I didn't realize that it was actually missing from this original piece over here. So whoever took the speaker out, they took that piece of metal with it. So I'll go ahead and get this speaker installed. I've already checked the impedance. It does check out okay, so it seems to be in working condition. So I'll go ahead and get this installed in here, and then let's see how the instrument performs. Alright, so the HP8920A is powered up. It passes its self-tests like before, so let's make sure that newly installed speaker is working correctly. Now it's set to the FM demodulation mode, and the squelch is turned all the way down, so if I turn the volume up, you can hear that rushing sound. So obviously the speaker is making some sounds, but let's make sure that it demodulates and produces a nice clear audio tone. Now I thought it would be a good idea to input a little bit higher RF power level than I did previously, just to make sure that the HP8920A is accurate in its power reading. So instead of just the signal level coming out of the RF signal generator, I'm going to run it through an RF amplifier. And that'll boost the level up a little bit higher. So pardon some of the background noise you might be hearing. There's a number of fans running. There's a fan in the 8920A, there's also a fan in the signal generator, there's a fan in the power meter, and there's a cooling fan in the power amplifier. And that power amplifier has vacuum tubes in it, so that's probably the noisiest fan of all. So I'll explain the test setup that I have here. So the HP8664A RF signal generator is set to 100 megahertz. I have the FM at 5 kilohertz deviation and the audio tone at 1 kilohertz. And it's set at minus 0.5 dBm output, and I'll explain why in just a moment. The output of the RF signal generator is going over to the Boomton. Also, this amplifier is made by Hewlett-Packard, but this happens to be the Boomton version, which is the early version. It's the model 230A RF power amp. The output of the signal generator is going into this RF amplifier, and then the output of the RF amplifier will be going over to the 8920A. So this is going to boost the output from the signal generator up to 2 watts. So 2 watts is equivalent to about 33 dBm. Now to make sure that it's set exactly at 2 watts, and then we want to see 2 watts showing up on the 8920A's display as well, I'm measuring the output on a Hewlett-Packard 8481H power sensor. Okay? So on that power sensor, it has a maximum input of 3 watts, which is about 34.77 dBm. So just to be on the safe side, we'll just go to 2 watts. I won't push that sensor right to its maximum. So 2 watts again is about 33 dBm. So right now what I'm going to do is turn off the RF signal generator and go over here and disconnect power sensor. It's definitely getting warm on its input side. Feel the heat building up a little bit there. And I'm going to reach around on this other side here. So the power sensor is on the end of the, or was on the end of this coax cable. So that will be the known power level, 2 watts going in right here. And the reason that the RF signal generator is set to minus 0.5 dBm is that's just the output that had to be set to cause exactly 2 watts, or very close to 2 watts, to appear at the end of this RF cable. Okay, so go back over here, let's turn this on. Alright, what do we have here? Perfect, look at that, 1.99 watts, awesome. So this is very accurate, extremely happy to see that. Now if I go over here, the modulation is turned on the signal generator, so if we turn this up, perfect, nice clear tone. You can see it's indicating 1 kilohertz. and the deviation, it says 4.9 kilohertz, and I have it set to 5 kilohertz, so excellent. Working very, very well. Now, as I mentioned earlier in the video, I've already gone through this test set and then checked out the various functions and features, and I'm not seeing any other issues, and it's passing all of its built-in self-tests. So not just the self-test when it powers up, but also the extensive self-test that you can choose to optionally run. So I'm not seeing any other issues. The problem was the lack of audio, and obviously the missing speaker was the cause of that. So it looks like this test set is fully functioning and it's ready to put into use on the workbench. So I'm very happy how it turned out. If you did enjoy this video, you can let me know by giving it a thumbs up. And if you're enjoying the content on this channel, don't forget to subscribe, tap the bell symbol to be notified when I do post a new video. Lots of projects coming up. I have several projects that just arrived here and they need some attention and some repairs, so we'll get into those. All right, as always, thank you for taking time to watch, and until next time, take care. Goodbye for now.